getting into like what I discussed in the beginning of the unit with the practical applications. That's what the next part's going to be within this unit. That is substrate utilization. What fuel source do we use during certain times of exercise? That is, which fuel source is the best to help resynthesize ATP to keep everything going. That's keep the ability to keep generate power to help us to keep moving. Okay, so remember substrates that we talked about: fats, proteins, carbohydrates. And so what we'll be getting in here is how does intensity impact fuel usage? How does duration, training status, and dietary history, how are all these going to go overall determine then what fuel source we're using for exercise? And so just remember those 4 points, and also just keep remember some of these relationships we talked about. Well, I already brought up a little bit with glycolysis. What happens when glycolysis works too fast? Well, lactate gets formed. We'll start talking about some other relationships coming up here. That is, what happens to protein breakdown with glycogen levels? Such as we decrease our glycogen content, protein breakdown goes up. It's almost a direct correlation. It's like a 0.99 correlation in terms of glycogen content, protein breakdown. So keep in mind, we're going through this next part. Just know we're framing it with everything we just talked about, the energy systems. And we talked about with all that. So that's why remember the advantages and disadvantages of those systems. Well, now we're going to be talking about how these parts of exercise, duration, intensity, training status, how much what we've consumed, how that's going to impact and what fuel source we're using. So remember, that's why I keep going back. Understand the energy systems. Once you get those down, this will carry then into the practical part of this unit that we're getting to now. Determining whether carbohydrate, fat, or amino acid is used for ATP resynthesis during exercise. So we're getting in here, like I discussed, what determines the substrate that will be used to maintain energy, that is ATP demands during exercise. There's 4 factors that we'll talk about: intensity, duration, training status, and dietary history. So first we talk about, this is what we refer to as the crossover concept. Okay, this is looking at the contribution of carbohydrates versus fat throughout different intensities of exercise. You can see at the bottom the percent VO2 max. And that crossover concept is basically the point at which, so normally at rest, let me refrain. So normally at rest, fat is a primary fuel source for pretty much everyone. Okay, for trained, untrained, fat is a primary fuel source at rest, and then somewhat is carbohydrate. So this is the basis of helping with cellular respiration, is using that fat during, you can see it's about, you can see the bottom down there, about 10-15% VO2. That's roughly a little more than that's about rest. We're never at 0% of VO2, because if we were, that would be death. And so you can see at rest, for the most part, it's fat being the primary contributor to ATP demands as opposed to carbohydrate. And you can see once you move away from rest, there starts to be a progression to where you start to decrease fats and increase carbohydrate. And the crossover concept's that point at which carbohydrates takes over and becomes the predominant supplier of ATP versus fat. And you can see that point right there is maybe 35% VO2 max, thereabouts, which if you look at what that is in terms of intensity, that's basically anything on and beyond being at rest. So anything from getting up and walking around is where you gets to that VO2. So really, you really start to switch over and become more carbohydrate dependent, anything outside of being sedentary, which shows you that how important carbohydrates are for the fueling of the body during exercise across all exercise intensities. And so this point is at which, like I said, the point where carbohydrates switches and becomes a predominant energy source. And it doesn't take much more than moving away from just being at rest where you start to become more dependent upon carbohydrates. And even at moderate intensities, it's roughly maybe, it's not, You can see it like 40%, which is a low intensity, to 60%. Those are low intensities. It's moves from 50% of each to a little bit, 60% carbohydrate, 40 thereabouts of fat. And so what I'm getting at with all this is that fats are important during low intensity exercise, yes, but it doesn't take much more than getting away from that low intensity where you start to become more carbohydrate dependent. And you can move that crossover point over, and those who train are able to move that point from, if it's about 35% VO2 max right there. I'm not sure exactly if we know exactly how far we can move that to the right, but those who are super well trained can move that over to a certain degree to the right. But still, even those who are trained, there's going to be a point where they become more anaerobic than aerobic. So this kind of falls suit for everyone. It's just those who are trained will have a different spot, but it's not like if you become super well trained, super high endurance, that your crossover point is going to be at 60%, 70% of VO2 max. It will never be to that point. But training does help move that point over to the right. But nonetheless, intensity is one of the first things that we've mentioned already, but intensity has a huge impact upon carbohydrate and fat utilization. The harder the intensity, the more carbohydrate reliance is on energy or ATP demands. So why does intensity, though, have this impact? Well, one reason is carbohydrates use more exercise intensities as intensity increases because the rate of glycolysis is faster than the rate of oxidative system. So remember, we talked about, this is lactate threshold here, but lactate gets formed when glycolysis works at too fast a rate. And so that does happen, but the benefit of working glycolysis is able to work at that fast rate is it supplies ATP faster than the oxidative system. And so main reason why we use carbohydrates at high intensity is because it could match the demands of ATP, the needed ATP to perform the movement. Okay, so the harder you need to go, the more carbohydrates will be available because glycolysis can supply those demands. And remember, the lactate threshold is the point where glycolytic processes in the cell are going faster than the oxidative process itself. It's now going into step number 2. Well, going back to here, we're talking about glycolysis working at that faster rate. It can supply the ATP demands. What happens when glycolysis works at a fast rate we've been talking about? Well, lactate does get produced. Okay, so brings us to point number 2, is that lactic acid, and I don't know if anyone knows exactly why this is, but lactic acid blocks or inhibits lipolysis. I'm not sure if there's a receptor that lactate blocks or what, but we just have seen, it just shows that as lactate gets formed, lipolysis gets inhibited. So yes, carbohydrates do supply the demands at those high intensities. That's good. But when glycolysis is working at that fast rate, you produce lactate. And the problem is from there, lactate does inhibit lipolysis. So that's point number 2, why carbohydrates are used at high intensity. And the third point says the third reason deals with the location of the substrate that's going to be used. Transport to the cells takes time. Hence, muscle glycogen is used first at high intensities or when fast rates of ATP resynthesis are needed because it's located on site. You can see the contribution, about 25% VO2 max. That is roughly, maybe rest for some. You see contribution, free fatty acids is the greatest amount. Very little muscle glycogen. But then 65%, which is really it's a decent pace to be training at. It's not super high intensity. It doesn't take much to get to 65% for those who are untrained. But you can see muscle glycogen and fatty acids splits to almost 50-50, thereabouts. But then you get to the high intensity, the one on the right, at 85% of VO2 max, it's all muscle glycogen. The reason being is because, remember, the glycolysis can be used at those fast rates, so it can supply those demands. But in doing so, you need to have the substrate available. And since we store glycogen in the muscle, which is where ATP is being used, it only makes sense then that's why I prefer carbohydrates, because they're located on site and they could be used in those high intensity type situations. Next is duration. It says exercise duration also impacts the choice of substrate. You can see right here, percent fat used and carbohydrate used. The longer we go, well, we use more fats a lot longer in exercise than carbohydrates. Reason being, it says the longer the duration, the less the carbohydrates used. And why is that? The reason being is that we run out of glycogen. Okay, the longer we go, we start to become more reliant upon fat because we just run out of glycogen. And you can see this intensity is for 65 to 75% VO2 max. And that's really, like I've said, that's not that hard of an intense workout. And you can see within about 20 minutes or so, 20, 30 minutes, you're starting to have a major shift in fat versus carbohydrates. That's because within about 30 minutes, and you'll see in the next few slides, you could start to deplete glycogen pretty quick, really, really fast. Okay, so just simply put, the longer you go, the more you use fat, just because you run out of glycogen. Problem is, though, is that your intensity goes down as well. Okay, if you're using fat like this, you're also working at a slow pace. So you're going longer, but you're slowing down because it just can't match the demands that keep you going. So you will slow down. Performance will be impacted once you start to switch over like this. This is the main reason for decreased carbohydrate use with increase in duration, decline of muscle glycogen. And you can see right here within about 20 minutes, you see that steep decline in muscle glycogen levels in a very short amount of time. And then with an hour and a half or so, you're basically almost fully depleted. And I keep saying this, but 65 to 75%, I mean, it's a good workout, don't get me wrong, but it's not like you're training at, super high intensity. It's a relative moderate to, high type intensity exercise, but it's amazing that within 20 minutes, a strong exercise stimulus could actually decrease glycogen that much. So that's why levels become so important when leading into exercise, because you want to make sure that you are fully glycogen stored up before you get going. It says when muscle glycogen is exhausted, then blood glucose falls. It says note that blood glucose never reaches zero. This is because the brain metabolism relies almost completely upon blood glucose. Hence, when glucose levels reach a certain point, the brain starts to shut down competition. The brain is like a stingy kid. Remember those kids that we all grew up with that didn't get their way? They would, steal your toys or steal whatever and shut down all the fun because they weren't getting their way. That's pretty much the brain. Because the brain, just like we learned in the past, but nervous tissue relies upon carbohydrate for fuel. And brain is nervous tissue. And so what happens is if you start to run out of glycogen, the brain will shut down everything that way. Basically to save itself. And the harder you work, the greater the intensity, the less amount of time you actually could go because you basically shut down everything because the brain needs to keep surviving. And so it'll shut everything down to make sure it gets all the glucose that it needs. It says during post-absorptive conditions and exercise, the liver maintains blood glucose levels. It does this through glycogenolysis and gluconeogenesis. Okay, we already talked about gluconeogenesis, but remember that's the formation of new glucose from a non-carbohydrate source. You got glycogenolysis, which is the formation of new glycogen. I'm sorry, my apologies. It's the breakdown of glycogen. Olysis break down glycogen. So you start to break down glycogen. And so the liver really helps maintain resting blood glucose levels and exercise levels as well. And it just does this by constantly making sure there's enough glucose in the blood at all times. So this graph says, once again, for the same intensities, you can see the relative contribution of energy expenditure. See muscle glycogen at the very bottom. Within a couple hours, glycogen's down, and at that point, you see blood glucose starting to increase as glycogen is going down. Reason being is because you're burning up everything within the blood and the muscle, so you're starting to see the reappearance of blood glucose getting out into the blood to maintain demands wherever it needs to go. You also see the increase in plasma-free fatty acids. Those are increasing the longer we go as well. Okay, yes, using fats is good because we're always thinking if we're using fats, we're burning fat and getting leaner. But make point here that if you're seeing a big reappearance of fatty acids during exercise, it's more or less because you have run out of glycogen. And keep in mind the relation between glycogen levels and protein breakdown. So yeah, you're seeing a lot of appearance of the free fatty acids in the blood. You're burning those, but you're also, if glycogen is going down the way it is, then you're also burning up a lot of protein to maintain oxaloacetate to keep everything going. In the top, you see muscle triglycerides. So the body is able, and this is a training adaptation, is able to store triglycerides in the muscle, which is a benefit because those triglycerides are on site, and you could use them right away to be used. Like I said, it's a training adaptation with that. This gets into what we talk about with the athlete's paradox. That is, athletes are able to store a lot of triglycerides within the muscle. Problem is, most athletes are really lean. So it's a paradox because they're able to store muscle or triglycerides in the muscle, but they're not able to use them that much because they burn them up too much because, you know, most athletes are really, really lean. So it's kind of a, yeah, you could do it, but it sucks because you can't use it because you can't actually store it up because you use them up too fast. That makes sense. Training status. It says carbohydrate utilization during exercise is influenced big time by the state of training. It says at the start of exercise, untrained people use more carbohydrate than trained people. Additionally, the untrained use the carbohydrate more in glycolysis than in the oxidative system. So those who are untrained will burn through their carbohydrates a lot faster because they just don't have the pathways to use fat. And so they don't have the enzymes, the mitochondria, the size, the number, the pathways, all of that to be able to use fat, so they have to use the carbohydrates. You can see the top one, glucose uptake between trained and untrained. You can see the huge uptake of glucose in the non-trained in the top one. But the problem comes in too, remember, what happens during times we're using primarily carbohydrate for fuel? Well, what gets produced? Lactate. So you can see the bottom down there, lactate formation, trained versus untrained. So this further makes them use even more carbohydrates, the untrained, because remember, lactate blocks lipolysis. So untrained will use mostly carbohydrates because one, they don't have the enzymatic pathways and the ability to use the fats, so it forces them to use more carbohydrates. But by doing so also produces lactate, which then in turn blunts lipolysis, inhibits lipolysis, I should say, which further makes them burn through the carbohydrates as well. And this is what I said right here. They just don't have the capacity for lipolysis, the untrained individuals. And so the top one, you see glycerol release, trained versus non-trained, greater release of glycerol, and then fatty acid uptake, greater fatty acid uptake in the trained versus untrained as well. So they're just showing you those who are trained can use fats during exercise a lot more than untrained. And this becomes beneficial for those who are trained because what happens is it preserves glycogen. And basically the untrained or the trained individual will use fats and they'll use just enough carbohydrates to supply, oxaloacetate demands and other demands, just enough to keep those processes going. And so those who are trained can go a lot longer in exercise because they're not burning through their glycogen all at once. They're having a slow decrease in glycogen over time. As opposed to those who are untrained, it's like going off a cliff for those who are untrained. Doesn't take long before they're at the bottom, run out of glycogen. But those who are trained will have a slow decrease in glycogen over time. So be able to use fats will preserve glycogen, will keep them going. And just always remember that last point. Fatigue sets in when carbohydrate starts getting low. Once you get glycogen depleted, you will start to slow down. Okay, all the enzymes or all the energy systems will slow down, thus causing you to slow down. Last, you got the composition of a person's diet. So this has a huge influence upon the percentage of carbohydrate and fat used during exercise. You see the top slide up there says, mixed diet of 235 grams of carbohydrates. Well, you can see they used X amount of free fatty acids and were able to go, about 180 minutes or so. Contrast then with the second one, the middle one, where those who are using, they had 400 grams of carbohydrate used. You can see this high carbohydrate diet consumption allowed them to go almost basically an extra hour longer than those who ate 235 grams of carbohydrates. And those who are in a low carb diet are not able to go, only about half of what the mixed diet were able to go. So what this is showing you is that if you're doing some kind of event that's really time-based and long endurance event, you need to make sure that you're consuming in a pre-competition meal a big consumption of carbohydrates. Okay, not an hour before, but we're talking leading up to the race. You want to make sure you get a lot of carbohydrates in. That will help you out. And you can see right here, those who ate a high carbohydrate feeding or a diet were able to go an extra hour longer than those who, still 230 grams of carbs is still a decent amount. But those who consumed far and beyond that were able to go almost an extra hour longer than those in the first group. I've already said this, but it says exercise intensity has an influence on the amount of protein that's broken down and used for fuel. And you can see right here, it's almost a perfect correlation, 0.986 between, you can see leucine oxidation, that's just a marker of amino acid breakdown, how it goes up along with intensity. So the harder you're working, which means the harder you're working, the more glycogen you're using, then is also directly correlated to the amount of protein being broken down. And just remember that. Glycogen levels and amino acid breakdown, almost a direct correlation. It's pretty close. So glycogen content will have a huge impact on the amount of amino acids being released. You want to maintain that. Don't burn through all your glycogen. Make sure you're trained, you consumed enough. That'll help out with limiting protein breakdown. It says the use of protein as a fuel during exercise is regulated by the amount of available carbohydrate. Remember, oxaloacetate can only be made from carbohydrate and certain amino acids. The top graph up there shows exercise time at a relatively moderate intensity. You can see protein breakdown starting to increase. And then once it gets to the top, you can see at that point where they start to feed glucose. Protein breakdown immediately starts to decrease just by feeding glucose, halfway through into the race or the competition. Okay, so protein breakdown will immediately start to go down right when you start to get the presence of a carbohydrate. And you get the bottom ones, you got sweat urea, nitrogen, so looking at just basically nitrogen balance there. Those who are carbohydrate depleted versus those who are loaded. And that's just a marker of protein breakdown. You can see those who are loaded, carbohydrate loaded, had a far less nitrogen excretion, that is far less nitrogen breakdown than carbohydrate depleted. Okay, there's always going to be protein turnover. So you're not going to get to where there's zero protein breakdown. The goal is to have, during exercise, the goal is to have as little protein breakdown as possible. And the best way to maintain that, consume carbohydrates. Okay, carbohydrate consumption will help supply oxaloacetate, will help limit protein breakdown. It'll help you keep performing at a great level and keep going for a longer amount of time. So make sure you're consuming enough carbohydrates. I'll get into all that, but definitely before, during, and after competition. So to recap, you got factors which influence whether carbohydrate or fat is the primary substrate during work or exercise. You've got the intensity. Remember, the harder you work, the more carbohydrates are being used. Reason being, because glycolysis could work at a faster rate than the oxidative system. Remember, those who are trained at high intensity will rely upon carbohydrates far greater than the fats, just because it can supply those demands at that greater need. And it doesn't take much more than just moving beyond sedentary before you start to really need to rely upon carbohydrates. Downfalls, though, well, you start burning through glycogen, but also remember, glycolysis is working at that fast rate. What also is happening? Lactate's being formed. And so that lactate formation will then inhibit lipolysis. So that's another reason why intensity impacts what fuel source substrate we use. And the last one's on site location. Okay, glycogen is located on site. So therefore that's going to allow for that to be broken down for fuel because it's being broken down right where ATP is being used, that is at the cross bridge. You got person's training state. Those who are trained will use a lot more fats because they have the enzymes, the pathways, and the ability to be able to use the fats. Those who are untrained, they don't have the pathways, they don't have the capacity to use lipids for fuel. So they have to rely upon carbohydrates. So they'll burn through their glycogen stores at a faster rate than those who are trained. But also what happens when you're using all these carbohydrates, just like we talked about in point 1 and point 2 of intensity, well, lactate gets formed, and lactate blocks lipolysis. So a person's training state, one, they don't have the capacity to use fats. Number two, the byproducts of using carbohydrates blocks that lipolysis even further. And then dietary history. Making sure that you are eating properly going into competition. So having a lot of carbohydrates, and those who play football in high school could all, attest to this. I'm pretty sure every single high school across the nation for the last probably 40 years or whatever, the night before every football game, everyone always has a spaghetti dinner. I don't care where you're at. Okay, we always have a spaghetti dinner the day before. Why? Well, because you're trying to get the carbohydrates in. So that's why it's important to make sure that you are fully topped off. The glycogen stores are fully topped off going into competition. That'll vastly impact performance. And so make sure you're getting enough of that in leading into competition. So remember these 4 points: intensity, duration, training state, and dietary history. All those will impact then what substrates being used during work and or exercise. Moving on, one thing that needs to be paid attention to is, we've talked about protein breakdown, but one thing in particular is the nitrogen balance, is what we refer to as, and that is, it says when a person has a large increase in their daily exercise habits, they usually go into a negative nitrogen balance. This is the relationship between protein break or synthesis versus protein degradation, protein breakdown that is. And so when you start a training session, the body kind of goes in the, I won't say a shock, but somewhat of, I call it a shock point where you start to break down way more protein than necessary. You start to go negative into a negative nitrogen balance at that point. So when starting a new training session, it's always a good idea to boost up the amount of protein intake. That way you can kind of bring that balance closer to at least a neutral. So a neutral balance at that point. Ideally, you like to be at least in the positive. That's where you're synthesizing more than you're degrading. But you'll see this even in trained individuals. Those who are trained for a while, when they switch up their training program, you add a new stimulus into the regimen, the body will start to go into this, like I said, a shock point where you start to then break down way more than you're building up. And that's negative nitrogen balance. And so, like I said, ideally you want to be at least in the positive or at least a neutral nitrogen balance. And the best way to do this is boost up the amount of protein consuming, especially when starting a new regimen. It says negative nitrogen balance is not uncommon when athletes who have trained at high durations and intensities. It says increasing the amount of protein in the diet can help alleviate this problem. However, not the only thing that needs attention. We'll get into that here in just a sec. But this graph right here is just showing young and middle-aged athletes, and you can see protein intake. And you get to the parts on the right there, so that 1.1 to 1.8 grams per kilogram. Well, those who are training more, whatever the case, intensity or duration, you see those who consume a little bit more in that 1.1 to 1.5, and really even a little bit more depending on what kind of athlete, that equals out to, roughly about 1 gram per pound of body weight. And that's usually the recommendation for athletes, is about that 1 gram per pound of body weight. And so it's important, though, if you're starting to switch up a program, or you've been training for a while, but you're just going super high intensity, durations, things of that for, add in more protein into the diet will help out. Okay, it'll help at least stay in a neutral balance. And if taking a little bit more than you need, then it could get you into that positive balance, which is where you want to be. Problem is, you look right there, it says the RDA says about 0.8 grams per kilogram. So that's roughly almost like, that's like a 1 gram for half your body weight. Might be the best way to look at it. So if you're 200 pounds, you're getting less than 100 grams in. Okay, the RDA, the recommended daily allowance, is far less than what athletes need. Athletes need that up to, they say 1.6 to 1.8 grams per kilogram, which is basically about 1 gram per pound of body weight. It's a good rule of thumb. So the other consideration is looking at protein in diet, but also making sure you get enough glycogen or carbohydrate in your diet as well throughout the week. This graph right here is showing at the start of the week versus the end of the week, muscle glycogen content. It says over the week of heavy exercise, muscle glycogen can experience a steady decline. So in other words, a person can use their muscle glycogen faster than they replenish it. And remember the relation to muscle glycogen and proteolysis. So this is basically showing you throughout the week how if you don't consume enough carbohydrates, as you keep training, keep practicing throughout the week, if the end of the week is when competition is, well, you're already starting to compete at a low glycogen level than where you were at the start of the week. Okay, so it's important. We talked about the pre-event meal, the dietary history, getting a good amount of carbohydrates before the event. But this is taking that a little bit further going throughout the week then, making sure that you're getting enough throughout the entire week. Okay, sometimes everyone's always worried about what they eat. Well, when you eat is just as important as well. Okay, those are fearful of eating carbohydrates. Well, you can see the relationship between glycogen content and proteolysis. If you're not consuming carbohydrates, you're going to just further that protein breakdown. Like I said, these type of athletes, like you said in the 5th day post, that is like the end of the week, sports like football. Well, if you're starting to play the game, you got to think that a lot goes into football, especially in South Texas where we're at. It's hot and humid. Okay, so you're burning up a lot of carbohydrates just from practicing, being in the environment all week long. But then the day of the game, you're nervous, which further increases carbohydrate usage. You could be starting the game at a half-empty tank. Okay, not a good idea to go on a road trip if you've got a half a tank. Doesn't matter really how far you're driving. Just make sure if you're driving somewhere, you want a full tank to go somewhere. Right? I'm not going to drive up to Houston or Dallas, something like that, with an empty tank. Or a half tank, even if that matter. So make sure throughout the week, you keep consuming, making sure as you're training, even if you're competing through the week as well. Okay, so maybe take this example right here, and let's say soccer, for instance. The average length somebody runs in the soccer match is, I think, 7 to 8 miles, something like that. That's a lot of work. So making sure those type of athletes, and they're usually doing a couple times a week on top of practice. So making sure those athletes need to keep consuming carbohydrates as much as they possibly can to keep the glycogen level as high as it possibly could be. So during an event now, it says ingesting glucose during exercise activity will help to reduce the loss of muscle and liver glycogen. The liver, we store muscle glycogen, remember the muscle and the liver. The liver is basically a reserve tank for glycogen. And so it says it takes 20 to 30 minutes for glucose to be absorbed into the blood. This will also reduce proteolysis. And you can see the bottom down there, those little arrows are showing some kind of feeding. And so they fed glucose about every 15 minutes or so. Yeah, it is actually every 15 minutes. And you can see the top graph right there, how glucose versus no glucose. You can see the top, the glucose feeding, you can see they're both going to increase because you got to think as you start to exercise, things are getting adjusted. So you're going to start using that blood glucose right away no matter what. But you can see once those who started feeding, once it got into the system, you can see it's a lot more maintained than the bottom one, the solid line, where it goes up and it just declines all the way down from there. Okay, so the top graph is just showing that blood glucose is maintained by consuming every regular through an endurance event. The bottom graph is looking at power up or work, so power. And you can see both are going down because as you're training, competing, if you're consuming some in, you know, it's still fatigue setting in no matter what, even if you are consuming it. However, the important part is that very last one where it shows at the very end at minute 110, that huge spike in work at the very end as opposed to no glucose. Well, think of this as some kind of endurance event. And what happens at the end of the event? When you see the finish line, what happens? You kick on and you give everything you possibly can for that last little bit. So this is where it becomes important. That regular feeding is one, it maintains blood glucose levels throughout the event, but then it gives you the ability to produce power when you absolutely need it, such as like at the end of the event, you need to just give that last little bit. You have just enough in the tank to, boom, get you across the finish line. And thirdly, also that last point. By consuming glucose regularly, it will help limit proteolysis. So it'll help limit protein breakdown. So it's important now. We've talked before the event, the day or so. We've talked about the week, throughout the week leading up to the event. Now I've talked about during the event. Okay, so important. All these parts are just as important. Okay, it's when you're looking at athletes and feeding, it's all about maintaining the proper amount throughout the entire time. It's just not that one day because most athletes are competing regularly. So you got to make sure you're feeding enough throughout the week to make sure performing at the optimal level. So one thing to be careful of, though, we talked about before the event, make sure you're feeding, but you want to watch what you actually are consuming in terms of carbohydrates. So it says ingesting glucose. So anything with glucose that is referred to as like a simple sugar versus complex carbohydrate. This gets into the glycemic index. So glycemic index is an index that rates foods on how high they raise your blood glucose levels. Okay, foods are simple sugars like Gatorade, honey, some fruits, white bread, things like that will raise your blood glucose really fast, and it will high amount and really fast. Complex carbs like vegetables, oats, some wheat breads, things of that sort will have a lower glycemic index, which that in turn will raise your blood glucose levels. It'll be a lot steadier of a release into the bloodstream of glucose. So the problem is when you have a high glucose food, with all glucose, you have a release of insulin. Insulin's job is to pull glucose out of the blood into the cell. And so what happens if you have a high glucose feeding, it says right here, 30 to 45 minutes before an activity, this will then hasten, that is, it'll increase fatigue. It says the glucose triggers a high insulin level, then followed by become hypoglycemic, and a faster than utilization of muscle glycogen. So it says, do not eat high glycemic index foods 30 to 45 minutes before exercise. And remember, once again, the glycemic index refers to how fast blood glucose will enter the blood and trigger a high insulin level. And you can see the top one, those who had no glucose versus those who had glucose. Well, a lot steadier of a release of glucose in the blood or maintain blood glucose, those who do not consume a high glycemic food going into the event, as opposed to those who consume some glucose. And you can see at the bottom, insulin levels a lot more maintained as opposed to those who consume glucose. Okay, so this is looking right before the event. Okay, you don't want to have this high glycemic food, an hour or so before the event. The goal is by the time you're getting that close to the event, your level should be topped off. All of your tanks should be full as much as possible. Okay, if you are going to have something, make sure it's a low glycemic food. And we'll get in here in a minute, but maybe fat or some kind of protein. That would be probably better right before the event than some kind of carbohydrate, because at that point, if you're trying to top off your tanks an hour before, you've waited too long. These high glycemic foods are good, though, during the event, like the last slide we just talked about, and after the event is good as well. Okay, post-exercise, your body's starved and it needs as much nutrition as possible. So after the event, it's good to eat a bunch of high glycemic foods that, boom, start filling up the glycogen tanks right away. Okay, but we're talking right before. Don't have any kind of high glycemic food. Limit that. And then during and after events when you want to have those high glycemic carbohydrate intake. You can see the top glycogen levels used as well. Those who consume no glucose don't use their glycogen as fast as those who consume glucose, that immediately right before the event. It says some research suggests that athletes do better if there's more fat in the pre-event meal. It says if more fat is available, then less muscle glycogen is used. You can see the top graph says no fatty meal versus fatty meal, and that's muscle glycogen used. So those who had a fatty meal used way less glycogen than those who had no fatty meal. And the bottom one, those who had a fatty meal used more fat than those who had no fatty meal. Basically what this is looking at is if you consume some kind of fat, and this is a good fat, not, as much as I love bacon and cheeseburgers and things like that, we're talking like almonds, avocados, peanut butter, something that's a healthy sustaining fat. Well, by consuming that, then your body during competition will be able to then start using that for fuel and preserving glycogen. And because you didn't have that glucose intake right before, you're not going to have the insulin response that you would with the high glycemic food intake. So having a fatty meal will then in turn allow your body to start using just enough glycogen to keep all the metabolic factors going, and that'll keep you going. So there's a lot of good evidence showing that fat is a good pre-event meal as opposed to carbohydrates. Now, leading into the event, this is assuming that your carbohydrate, your glycogen content is at capacity. You've already got the tanks full and ready to go. It says work endurance is related to the amount of muscle glycogen at the start of exercise. And this one is going off that graph we show with the mixed diet, the 400 grams, and the no carbohydrate intake. You see glycogen content and duration of exercise. So this is looking at this relationship, and they found that diet alone cannot control the amount of stored glycogen. So there's another way that if you want to store more, you have to go through. Okay, it says work endurance is related to the amount of muscle glycogen start of exercise, and that's correct. The more glycogen you have stored up, the more endurance, the more work can be completed. But then the question is well, how do you get that greater storage of glycogen into the muscle? And this is where we get into, I'm sure you've all heard this, but glycogen loading, carbohydrate loading. Those who have seen The Office, they saw Michael Scott before the rabies 5K run. He ate a bunch of Alfredo trying to load up. You've all heard it at some point or another. That's not how you do it, by the way. The Office episode where Michael Scott's eating that right away, that's the wrong way to do carbohydrate loading. So it says, let's get into this. So muscle glycogen levels will increase, supercompensate only after the initial levels are depleted or greatly reduced. So how do you store up more glycogen? Well, you first have to completely deplete the glycogen, and then you'll be able to store up more by consuming more after the depletion, is the basis of what glycogen loading is. And here, the graph, you can see the two different lines. One is one leg and the other is the opposite leg. And so what they did in this study here is they would basically have people just do one leg cycling. and then they fully deplete, and then they store back up, and you can see the leg that actually depleted, which would be the black line, that one depleted. Then following a few days of high carbohydrate consumption, you can see the glycogen storage was much greater than the leg that didn't do the depletion. Okay, and there's some kind of mechanism that once you fully deplete glycogen to a great degree, you're able to store it back up, assuming you eat a significant amount of carbohydrate. It says the amount of carbohydrate in the diet will influence the rate of the load. The recommended intake is 10 grams of carbohydrate per kg of body weight, which is an incredible amount of carbohydrates to take at one time. It says smaller people, such as like females, do not eat enough carbohydrates to begin with. So it's hard to have females, especially like this one right here, 50 kg, 110 pound female, such as like a gymnast. It'd be hard for them to get a lot in because they'd have to get 2,000 kcals of carbohydrates in just to meet these recommendations. But if you want to get the loading take place, you need to eat first you have to deplete, then you have to eat that 10 grams of carbohydrate per kg to get that super high amount. Here's a couple ways that they do glycogen depletion loading. Now I should make a point right here. Glycogen loading is only going to be beneficial for really endurance type athletes, those who need that high glycogen storage but are competing, every few months kind of deal, or you're getting ready for that one endurance race and sometime in the future. Normal athletes shouldn't be doing this all the time. Like, there's no point in football player doing this because, one, metabolically, they don't really need it, and two, it's not feasible. Just like soccer players, basketball players. So a lot of those athletes, the procedure one is just going to probably be the best for them, the one on the left right there. So you can see that one's just eating a mixed diet and then increasing carbohydrate intake leading up to competition. Another way, procedure two, is you eat a mixed diet, and then you do work, that is you deplete, and as soon as you get done depleting the glycogen, then you start to eat that high amount, and you can see the glycogen loading goes up even more. But if you're that endurance athlete that's training for that, that marathon, training for that race a few months from now, or some kind of cycling race or something like that, what you would do is eat that mixed diet. This is procedure 3. You do your work, so you deplete, and then you go a few days of no carbohydrates, eating only fat and protein while still training. And then you can see a few days before competition, you stop all of training and you eat that 10 grams per kilogram of carbohydrates. You can see how much greater the glycogen storage is at the procedure 3 versus 2 and 1. Actually, procedure 1, you actually didn't deplete glycogen. You just ate a higher amount than you normally did. So these are different procedures based upon the athlete. For most athletes, I always say recommend, like number 1 is probably the best, just increase your carbohydrate intake. That should be sufficient for most athletes, just making sure you're eating enough before the event, during the event, after the event, and throughout the week leading up to the next competition. It says glycogen supercompensation, that is glycogen loading, is regulated by the volume of carbohydrate eaten and duration and magnitude of the initial glycogen depletion. So the greater the loading is going to be dependent upon the magnitude and duration, that is how long and how hard you do the initial glycogen depletion. So that procedure 3, that's why you're depleting for work, and then you're going a few days of depleting even further because you're eating only fats and protein, and then you stop all training, and then you boost up your carbohydrate intake from there. So you see in procedure 3, those 3 or so days before the competition, there's no training whatsoever. Procedure 2, they might, a lot of times on that one right there, actually I should say procedure 2, they're going to work, deplete, and then at that point just eat carbohydrate right away for the next few days. And there's usually no training leading up to that competition day. Procedure 1, you wouldn't stop training. You just keep training, keep eating, and just keep that going. But this could be you could really do this any which way you think is going to help out with the needs of your athletes. Okay, and this is up to the coach to figure out the best approach to this. I wouldn't recommend this for anyone. I mean, I would say do this for those who are really trained are capable of being able to do this without hurting themselves. Okay. You can also do glycogen supercompensation in the liver. At least we've seen in animals. It's kind of hard to do in humans. No one really wants to give a liver biopsy. Ugh, that wouldn't be the best to cut a piece of liver out and test that. But we've seen in animals and rats. And so we assume then I guess in humans could do the same thing as well. Okay, the liver is a reserve tank for glycogen for the body, for carbohydrate storage. So if muscles could do it, there's no reason why we shouldn't, I guess, assume that the liver could do it as well. Okay, so which substrate to use? It says carbohydrates the preferred substrate for exercise metabolism. And remember this, it's so important. You run out of muscle and liver glycogen, work rate slows down, which translates into you slow down. Okay? Carbohydrate is what we want for exercise. And when we run out, then we run out. That means our metabolism slows down, which means we slow down. Can be used in 2 out of 3 pathways, glycolysis and the oxidative system. Can resynthesize ATP without oxygen. It's stored on site. That is muscle glycogen. It can be made, so gluconeogenesis in the liver and resting muscle. And I've said this, please remember this, it can produce oxaloacetate. This keeps Krebs cycle going. So especially if the acetylcholates are coming from fats, matches with oxaloacetate here, keeps Krebs cycle going, and allows you to preserve glycogen and also preserves amino acids. So that's why carbohydrate is preferred substrate for exercise metabolism. It's not preferred for storage though, because per glucose molecule, we store 3 water molecules as well. So there's limited room. That's why if you've ever had a high carbohydrate meal, usually after like a spaghetti dinner, a lot of bread, you feel kind of squishy, I guess, because you've eaten all those carbohydrates and well, it's stored with water. So therefore you feel poofier and fuller because, well, all the carbohydrates being stored with water as well. Okay, so we don't prefer storing it because we can only store so much carbohydrates. There's only so much room before we run out of space to be able to store more. However, I've already brought this up, but fat is preferred storage substrate. There's unlimited storage space for fat. Okay, it doesn't have to be mixed with anything. You can store it dry, basically. And I always use this example, but fat is like that nasty, dingy hotel in the middle of a downtown of a city. Okay, those ones you always see in the movies or driven by maybe, and it's those hotels you would never want to stay at. Those hotels always have that sign that says vacancy. They're never filled up. Those dirty hotels and cities never run out of room because, well, you can never fill them up. That's basically what fat is. Okay, there's a reason why, and I say this I'm not making fun of anyone or, trying to degrade anybody here, but we've all seen the show on TLC, My 600-Pound Life. Okay, there's a reason why people could get to be weighing 600, 700, 800 pounds is because there's an unlimited ability to store fat. The body is usually in a survival mechanism, and it doesn't understand that when you consume a meal, there's, at least in modern day America, there's going to be one here in a few hours. A lot of times. So the body keeps storing up fat because it wants to protect itself because it never knows when this next meal is going to come. So that's why fat is the preferred storage substrate, because we can store unlimited amount of it to help protect us for a time of starvation. Now, during, thousands of years ago when we didn't eat every single 3 hours, this was a good thing because we were able to store just enough up to keep us going to our next meal, because there really was a long time before our next meal. Problem is, modern day America, well, unfortunately, we have more meals than we need, and so we eat a lot of these high-fat meals, then we store the fat. We don't really need it, so we just keep adding on when it's not necessary. So that's why we do prefer as a storage substrate. Another reason why unlimited storage space is that you get more ATP per stored carbon. So if you're looking at a 6-carbon fatty acid, you get about 36 ATP from that. You go through the math right there. Compare that to the 6-carbon carbohydrate, glucose. You yield about 30 ATP. So you get some more ATP per carbon length compared to the carbon length of carbohydrate. And usually your fatty acids are much longer than 6 carbon, so therefore it's even greater amount of ATP. So there's that high dense energy storage substrate that has the ability to store unlimited amounts. However, fat utilization is dependent upon oxaloacetate. So fat must burn in the presence of carbohydrate. If you run out of carbohydrate, then OA can be made from amino acids. You never want to get to that point. But just remember those relationships there. It says low carbohydrate availability leads to protein breakdown. So if you want to limit the amount of protein breakdown, eat more carbohydrates. If you want to limit, remember, you want to limit the amount of ammonia being produced. Okay, how do you limit ammonia? Well, talking about substrate and food consumption, eat more carbohydrates. That'll stop protein breakdown. Another thing you can do too is increase creatine phosphate intake, supplement with it. Going back to the first energy system, the immediate system, and when we run out of carbohydrate, or creatine phosphate, you switch to the mild kinase system, and then you start to then build up AMP, and then you turn into monophosphate ammonia. Well, consume creatine monohydrate. That'll help out limit protein breakdown as well. And says the point is like this: protein is used for energy when carbohydrates low. You never want, and I keep stressing that you never want to get to that point where you are using protein for energy. So to maintain proper function, eat a lot of carbohydrates, consume creatine monohydrate. Need to be that'll limit protein breakdown and keep operating at the same level that you're able, or that you want to be able, or the desirable level, keep operating at. It says, and also if you get to this point, low carbohydrates, says make glucose via gluconeogenesis, make oxaloacetate. Okay, so it's a costly process to be making glucose via the gluconeogenesis. So you're using up more ATP to do that, so you're putting yourself in a negative even further. So just make sure that you have a proper amount of carbohydrates because it keeps helping out. Well, one, you don't need to use a costly energy to make new glucose. And two, I keep going back to this, the carbohydrate allows fats to keep being burned because the carbohydrates supply the oxaloacetate needs, limit protein breakdown, keeps the acetyl-CoA operating properly from the lipids. Everything keeps working at a functioning rate at that point. To wrap up substrate utilization, remember, when we're talking about substrate, we're talking about fat, carbohydrate, and proteins. And when we're discussing this is, remember, what circumstances do we use those different fuel sources? Primarily fats and carbohydrates. You never want to be in a place where you're using protein. And so, with that being said, remember, what determines if we're using fat or protein? You got intensity, duration, training status, and dietary history. Okay, remember, with intensity, you've got glycogen works at a faster rate, or glucose or glycolysis works at a faster rate than the oxidative system, so therefore, intensity, you use more carbohydrates than fats. Also, with intensity, with the glycogen usage, the high rate of glycolysis, you're producing more lactate, that's inhibiting lipolysis. And then also, carbohydrates are on site, so therefore, less transport. Being on site means fuel is readily available to be used. Okay, so the harder we work, the greater the intensity, the more carbohydrates are being the contributor to energy production, ATP resynthesis. Okay, the longer we go, we use more fats. That's just because we've run out of glycogen the longer we go. Training status. Those who are trained are able to use fats more because of enzymes, pathways, and just the transport and the ability to use lipids more than, be able to use lipids at a greater rate. Okay, and then of course, the untrained use more glycogen because they don't have the pathways, they don't have the ability to use it, use the fats, and also the more they use glycogen, the more they produce lactate, that blunts the lipolysis even further. And then lastly, dietary history. Okay, consuming more carbohydrates leading to the event will then allow for a lot greater performance. That gets in then to remember, glycogen is important for performance. It's a great predictor. It's one of the best predictors for performance. And that is the greater glycogen storage, the lot longer somebody can actually go in training. They can use more fats as well, preserves glycogen. So it's important, not only, it's important to remember to eat after the event, during the event, and leading up to the event. All throughout, making sure the glycogen stores are at the optimum level. Because glycogen is the preferred energy for exercise. Fat is a preferred storage form of energy. Carbohydrates are preferred fuel uses during exercise. Okay, so remember, it's important to make sure those glycogen stores are leveled off all throughout training, but primarily leading into competition. You could do glycogen loading, those ways we talked about in that. That could help out depending on the athlete. But for the most part, just make sure you are consuming enough glycogen throughout the week. And also after training, during training as well, just remember the relationship between glycogen and performance, glycogen and proteolysis, that is a protein or the breakdown of protein. It's almost a direct correlation. Okay, how do you stop protein breakdown? Make sure you eat enough carbohydrates. Make sure you take creatine monohydrate. All that will help limit protein being used for fuel. Okay, so just remember, substrate utilization. The biggest thing is we want to use carbohydrates because that's the preferred energy substrate. What's going to influence that even more? Intensity, duration, training status, dietary history. Okay, remember all the things we talked about in terms of why carbohydrates are important. Fats are important for storage. They provide energy, but they don't provide it at the rate we need during most activities. Okay, so just remember what we talked about, all these different areas of substrate utilization, why and how we use which ones we do, and the importance of all of them. And then just remember just these relationships we talked about. Glycogen content versus protein breakdown. Okay, glycogen versus performance. What happens when we run out of glycogen? And OAA, oxaloacetate. Why is that important? Remember, OAA keeps Krebs cycle going. It comes from glycogen, or from glucose, I should say, and amino acids. So just remember all these relationships we talked about because this will vastly impact performance. And just keep everything, like I said, simplified. Know the importance of what substrate to use and how and when we use all the different substrates during the different types of exercise, and just overall those major influences upon substrate utilization.